where we go with it. Before you do any kind of antiderivative stuff, any fundamental theorem of anything, what I think we want to do with number 6 is rewrite it so that it's the integral from 1 to 2 of x to the negative 2 minus x to the negative 3 dx. Let's talk a little bit about what you can and cannot do with this. You cannot add those two terms, right? Because they are unlike terms, so please don't be tempted to try to combine those two terms in just a single x to the whatever. Just not going to work because they're unlike. We don't want them to be fractions. That's the whole point of flipping them up. And so once we have it to this place, we need to go term by term and find the antiderivatives. What rule would we use to find the antiderivatives? Drew?
Plus 1 and then divide by the new numerator.
Yeah, by the new exponent, right? Yeah. Yep, exactly. So I don't really think you have to show this step, but let's go. I'll show it anyways, just so you can kind of see what Drew was describing. The antiderivative would be x to the negative 2 plus 1 over negative 2 plus 1 minus x to the negative 3 plus 1 over negative 3 plus 1. So I'm just literally doing the power rule for integrals and showing that little step, but that in no way is that required, right? Because I knew you all can like add one in your head. No, not a big deal. At this point, I have found the antiderivative, and so I would want to say evaluated from 1 to 2. Notice that the tall skinny s and the dx are gone on this step. Why are they gone now? I did it. Yeah, I did what it told me to do. So if I've already found the antiderivative, I don't need to leave the tall skinny s there, the integral symbol, because I've already done what it asked me to do. Okay. It means evaluated from this to that. Evaluated from 1 to 2. Yep. It's probably not that big of a deal. I think it's good to kind of keep things straight. It's what it literally means. But I'm not going to go in there and be like, oh, sorry, didn't have the straight line. Where I think it could be confusing is you might, like I'm just thinking about in the hustle and bustle of a quiz or a test, you might mistake it for an exponent or something. So I'd be careful with it from that perspective, but not the end of the world. Okay, so let's go ahead and write down what this really is. This is really negative x to the negative 1 plus, 1/2 x to the negative 2? Make sense? So you could just jump straight to that. Evaluate it from 1 to 2. That would be okay if you did. So now let's use the fundamental theorem of calculus part 1. And this is the thing that's in the video. I noticed that my video count went from 22 to 27, I think. So 5 more people watched it. We're still about 25 or so people short. You should go back so you understand fundamental theorem of calculus. It's a 6-minute video. Invest 6 minutes of your time, and hopefully that'll be well worth it for you. No, no commercials, and that's, to be honest with you, of it. At this point, you know what? Let's talk about how points would work on a quiz here. Like these steps right here, like this one that I'm highlighting, this one that I'm highlighting, those are good steps, and I think that they might be very, very helpful for you. But I'm not going to tie a point to you showing that. Really where the first point would come from would be to show that you have the antiderivative in some form or fashion. So whether you did it like this or did it like this, if you have the antiderivative, I'm going to award that point because I'm going to say you clearly understand the calculus of this part, right? And then we'll see how it goes from there. So the second point here would be showing that you know how to use fundamental theorem part 1, and that's going to be the plug-in. So it's going to be negative 2 to the negative 1 plus 1/2 times 2 to the negative 2 minus the same thing just with the 1's plugged in. So it would be the negative of 1 to the negative 1 plus 1/2 times 1 to the negative 2. So that would, to me, would be worth a second point because you clearly showed the calculus concept of I know how to do FTC 1, Fundamental Theorem of Calculus Part 1, and that's definitely worth rewarding, right? Now what follows is maybe just a touch discouraging on the volume versus point ratio because to finish this, I'm going to give you a point. And it's going to involve some fraction work and all those kinds of things. And if you're like me, every now and then you just mess up a fraction. You mess up some arithmetic. It just happens. I don't want that to cost you like 3 points. Because it's arithmetic. If you mess it up, I want it to cost you like a point instead of multiple. Okay? Question before we finish.
Yeah, if I skip like what you just wrote out and just write like negative 1 plus like 1/2. Yeah.
So you're like automatically doing the evaluations with the ones or whatever? I think to some degree I'm okay with that. If all of that devolves into, and the answer is 3 or whatever it is, I'm not okay with that because you didn't demonstrate FTC 1. Does that make sense?
Yeah.
So I need some kind of concrete evidence that you know what gets plugged in where and subtraction and all that
So
stuff.
I said like.
But yeah, I mean,
half,
do you know that 1 times 1/2 is 1/2? I think I'm okay with that. Yeah. But just let's not let it get to the degree where you do all of it in your head and you're like, oh, the answer is 2.
Okay.
Done. Right? Show evidence that you used FTC 1. Okay, so let's try to finish this. So this ends up being negative 1/2. There we go. Negative 1/2. What is this 1/2 times 2 to negative 2? How does that end up finishing?
1/2 times 1/4.
Which is 1/8. Good. Minus, this is negative 1 plus 1/2. Okay, so to finish this out, maybe the best way to do it would be to distribute that minus sign throughout those parentheses. If I do that, I get negative 1/2 plus 1/8 plus 1 minus 1/2. Does that make sense? Do you see all the cancellations? Doesn't this and this cancel with that? They just add out completely and you get 1/8. So how'd that work out for you guys? Would it be fair to say that without the calculator, isn't the arithmetic almost or maybe as difficult as the calculus? So be careful. Be careful there. It's worth a point. Point is worth fighting for. But know that you'll be rewarded more for the calculus than for the finishing of the arithmetic stuff. Okay, so get your calculators out if you don't already have those out. I would like for you guys please to graph our function 1 over x squared minus 1 over x cubed. And I want you to try to decide on the interval 1 to 2, does our graph make sense with our answer of 1/8? Does the graph make sense? Or does it not? Is there some kind of a disconnect? Check it out, see what you think. So when you guys look at your graph, are you guys seeing something like this? If you get your y min and y max like it maybe plus minus 1. Okay, so first of all, yes or no? Does 1/8 make sense for an answer?
Yes.
What about the graph tells you that 1/8 makes sense?
It's about the area, pretty small, so, right?
Okay, yeah, very small. We had to zoom in a bit to see this. But what else about the graph tells you that 1/8 makes sense? I agree that the smallness does make sense.
The y value that 2 is 1/8.
Is it?
0.125.
Oh, interesting. But I bet you the y value at 1 is not.
It's 0.
It's 0.
Okay, keep thinking. Like what else about this graph tells you that 1/8, something about 1/8 makes sense? Think very simplistically. I would say the fact that 1/8 is the y value at 2, that's even maybe a little too detailed. What aspect of this graph tells you that positive 1/8 makes sense? Yeah, it's always above the x-axis, right? So what if we had graphed our function and on our interval right here, the whole graph was below the x-axis? Our answer should be negative and it was positive. Do you see how there would be a contradiction there? Some kind of a problem, some kind of an issue. But the fact that our graph is clearly above the x-axis for the entire interval, the 1/8, the positive 1/8 makes sense. And yeah, the fact that this is a very tiny graph, like it's pretty close to the x-axis, goes with the 1/8 idea as well. So let's look at it from this perspective. If we drew a little rectangle, and I didn't know what the y value at 2 was. If I drew a rectangle like this, let's try that. Rectangle like that, what would the area of that rectangle be? I used the height at 2 for my height of my rectangle. It'd be 1/8, wouldn't it? Wouldn't it be 1/8 high and one across? So do you see how part of the curvy graph goes above and yet part of it is below? So let's do this. I hadn't planned on doing this. Get back to your calculators and go back to your y equals. Leave this curvy graph where it is. Leave the window the same. Hopefully it looks about like that. And in your y2, will you guys write y2 equals 1/8? That should show you the rectangle that I'm talking about. And so if that rectangle really is 1 by 1/8, the area would be 1/8, wouldn't it? Do you see how the curve has part above and part below the rectangle? So again, I'm just trying to get you guys to see, okay, this actually does make sense, as opposed to there's this magical thing and it just pops out an answer, right? So that's the whole point of the calculator here. Any follow-up questions or anything you're curious about? Okay, fair enough. Well, let's go ahead and move on to our next one, the one with all the trig function stuff in there. Yeah, maybe. So with number 7, you look at that integrand, and isn't that integrand just a little bit intimidating?
A little bit.
A little bit, yeah. Do you recognize it as relates to any derivatives that we've ever done? Isn't that the derivative of cosecant?
No.
So if that integrand truly is the derivative of cosecant, then the antiderivative of that should be cosecant. So use that fact to help you as you proceed here. But knowing those old derivative rules and kind of the current integration rules should help this be a whole lot easier than it looks at the start. So I'll let you guys go from there and see if you can finish it. We'll do kind of the same thing with the calculator when we're done. Knowing that your antiderivative is cosecant, I think we can jump straight there, right? And then evaluate it from pi over 4 to 3 pi over 4. Again, I think you can do this without a calculator. It's not the easiest, but I think you can do it. We're going to use FTC1. So that would be cosecant of 3 pi over 4 minus cosecant of pi over 4. And here's where our friend the unit circle becomes something important. Let me put it to you like this. Cosecant is the reciprocal of what other trig function? Sine, right? It's just the reciprocal, the flip of sine. So what is sine of 3 pi over 4? 1 over root 2. Yeah? So then cosecant of 3 pi over 4 would be? Root 2. So square root of 2 right here. Minus cosecant of pi over 4. We're really talking about the same reference angle, aren't we? Just in the first quadrant instead of the second. And so is it really the only question comes down to, is it going to be positive root 2 or negative root 2? It's positive because we're in the first quadrant. So it's going to be root 2 minus root 2. So, wow, 0. That's an interesting answer, right? Because remember, indefinite integrals have to do with areas. So how could you get an answer of 0? Take your calculators, like you did before. Please graph this. Do you guys know how to do cosecant or cotangent on your calculator?
No.
Cosecant, you do 1 over sine of x.
Oh, yeah.
Cotangent, 1 over tangent of x. Please restrict yourself to the domain pi over 4 to 3 pi over 4. And again, let's see if you can understand, does the graph support our answer of 0? And if so, what part of the graph does, or what part of the graph contradicts getting an answer of 0? Yeah, it almost looks symmetrical, doesn't it? Yeah, so you've got part of the area above, part of the area below, so to some degree they should cancel out, and it appears maybe they completely cancel each other out to get a 0 there. Okay. It was a pretty graph. I agree. Okay, so let's do a little review of what we have done. We have done antiderivatives and definite integrals with a lot of stuff. We've done trig functions like we just did. We've done some fraction work where we had to flip fractions up. We've done radicals, square roots, and stuff like that where we've manipulated those. But we have yet to do number 8, right? Absolute value. So we're going to take a look at that. I'm going to show you 2 different ways to do it. We'll make a judgment as to which way is better, and we'll kind of move forward from there. So take a look at number 8. Do this one with you guys. Please notice a couple things. First of all, this is absolute value, but it's absolute value of a line, right? Absolute value of a line. And so that's very, very helpful. I'm going to show you how you could use a graph first, and then we'll look at the piecewise idea. So with a graph, let's see if we can figure this out. Since it's absolute value of a line, what's the general shape of the graph? It's going to be the V. Okay, I agree. Where's the little pointy part of the V going to be? 1, negative 1. You said 1, 0. There's some disagreement, isn't there? Do you guys remember that a really old-fashioned way of graphing things is to just go input, output? Plug some numbers in, get some outputs, things like that. What would you suggest for an input if we were going to just, we don't know exactly where this is. 0. Okay, so if you plug in a 0, 0 happens to be on our interval too, right? So that's good. If you plug in a 0, what do you get out? You get out a 1, don't you? So I'm going to say 0, 1. I'm going to say that is right about there. So 0, 1. What other number on our interval might you plug in? 1 or 2, I agree. So if I plug in a 1, I'll go with a 1 right here. Actually, sorry, let me rescale this a little bit. Let's go with a 1 right there. So if I plug in a 1, what comes out?
0.
1.
1. Right?
Oh, yeah.
2 minus 1, we get a 1. So for those of you that were saying, hey, I think the pointy part is at 1, hey, listen, haven't we just sort of disproven that? If you're saying, hey, I think the pointy part's at 1, based on the 2 points that I have up there, there's no way the pointy part's at 1, is there? It's actually at 1/2. It's at 1/2. So if you plug in a 1/2, what do you get out?
0.
A 0. So 1/2 comma 0 would be right about there. That's actually the little pointy end of the V. What other number might we plug in?
2.
2. That would complete the interval, wouldn't it? So I'll plug in a 2. What do we get out if we plug in a 2?
3.
3. So I agree with you on that. So there is my V. I'll try to connect with a straight line. There we go. So there's our graph.
Do you not finish, you don't do anything on the left, you just do the interval?
So I'm just going to be concerned about my interval, right? We could keep it going, nothing wrong with that, but I'm only going to be worried about my interval to do this. So the fact that this is a linear absolute value is very, very handy. Let's remind ourselves what an integral really is. An integral is an infinite summation, infinite sum of these little rectangle areas, right? So if you look at something like this and you think, wow, integration, I'm not sure if I want to do that. We can actually accumulate the area. Okay, we can accumulate the area. And what's so convenient about this is what are the shapes that are going to be involved in finding area? 2 triangles. So here's how we do this. I'm going to highlight the areas. So like right here, this little green area. And then of course, oops, let's not do that. I pushed the wrong button. There we go. And then of course this larger green area over here would be the other area that we'd be interested in finding. So let's try to find those areas. So for the little triangle on the left, what is the base length?
1/2.
And what is the height?
1.
So the area, 1/4, right? 1/2 times base times height. Okay, so for the triangle on the right, what is the height there? And the base? 1.5, or maybe 3/2 would be a little bit easier to use. So I'll go with 3/2 for that base length. So what's the full area? 9/4? Yeah, 9/4. Okay, so here's what we could really do with this. If we understand how area works with definite integrals, I could then immediately say the integral from 0 to 2 of absolute value of 2x minus 1 dx equals 1/4 plus 9/4, which is 10/4, which is really 5/2, 2.5, whatever. And that would be it. So let me encourage you to use that method when you're dealing with a piecewise linear absolute value. It's definitely the way to go. Much, much easier just doing a couple of triangular areas or rectangular areas or whatever they are and adding up the areas and you're good. So does that answer make sense? The fact that it's positive
Yeah.
because the graph is always above the x-axis. Yeah, if we somehow got a negative answer there, it makes no sense. So just a way to kind of self-check a little bit. All right, I'm going to show you the other way, show you that it maybe kind of works, but I'm going to try to persuade you to use the area. So here we go. If I'm going to try to create a piecewise graph, which is really what an absolute value does, I've got to create 2 pieces. One piece that was affected by the absolute value, and the other piece was not. So I'm going to create some intervals here. I'll base it like this. I'm going to highlight this. So if I highlight this piece in yellow, and then I highlight this other piece in a nice green shade, which piece was affected by the absolute value, the green or the yellow?
Green.
Yellow was affected. Here's why. If you took away the absolute values, wouldn't 2x minus 1 just look like that?
Oh, yeah.
Positive slope, -1, y-intercept, yeah. And so the green was unaffected, but the yellow was affected. So here's how we would do the piecewise. We would say f of x equals 2x minus 1. This is the part that was unaffected. If x is greater than or equal to 1/2. That was the part that's not even bothered by the absolute value at all. The other part is, and I would say that is, if x is less than 1/2. What would that piece have an equation? Like, what would the equation be?
Would it just be once you find the slope of what that piece of the line is,
Yeah, we know what it is though
I
already.
guess,
That's
negative
1/4.
Negative 2x minus 1.
Close.
2x plus 1.
Plus, you distribute the minus sign. Yeah, so it'd be, and you can see the y-intercept there is plus 1, right? So negative 2x plus 1. If you distribute a minus sign, that would give you this piecewise graph. We're not done yet though, right? Now we actually have to integrate. So here's what this would be like. You'd say integral from 0 to 1/2 of the affected part. So 0 to 1/2 is, that's the affected part. So negative 2x plus 1 plus the integral from where to where?
1/2 to 2.
1/2 to 2. Now we're doing the part that was not affected. So that would be 2x minus 1 dx. And that's set up pretty well, but you all know that we're not even done yet, right? Now I've got to find an antiderivative for the first one and an antiderivative for the second one. And then I've got to do fundamental thermocalculus on the first one, and then again on the second one. And then I still got to add up all the stuff that I get, right? So I'm going to finish right there because I know you could do the details if you wanted to. My point is, at this point right here, I've already taken more time than I did with the triangle thing. And I'm not even really, maybe I'm halfway done, possibly, but I'm definitely not done. So let me just encourage you, if you run into anything like this, draw a graph, pop points as needed, draw a graph, and just find the rectangular areas. Should be a lot easier for you, okay? And let me tell you, that is a totally legitimate way to do it. It's not like, oh, this is our way to do it. The AP folks would never excuse this. It's totally legitimate as long as it's lines. If it was curvy stuff, not so much. You're going to have to do the piecewise junk, right?
But if it's like a square,
Rectangles and triangles were good, right? But if it's curvy, right? If it's a parabola that's been absolute valued or something, the whole finding the area thing just doesn't work. So, because we don't have a geometry formula for the area of a parabola. All right. We good? All right, we've got a little bit more to go here. We'll be done soon. You guys are doing well. 3. This first question, is he with us?
Yes.
He is with us. Okay, I just couldn't tell. I don't know when you first would have done this, maybe like 5th or 6th grade, but how do you find an average? That's right. You're right. Add up all the numbers, divide by the number of numbers. So let's actually write that down. So how do you find an average? Add all the numbers, then divide by the number of numbers. Divide by the number of numbers. There we go. So it's always been true. That's the definition of an average. It's always going to be true. But we're going to be exploring some more advanced ideas about averages here in a second. So to kind of lead us into that, I'm going to ask you guys, I asked you this question the other day. I gave you the answer. Let's see if you remember it. What is an integral? Infinite summation. That's right. We talked about that a second ago as well. So it's an infinite summation. Keep that in mind as we talk about what comes next. So to find the average value of a function, let me set this up for you. If I have some function, who knows what it stands for at this point, but let's just say we got some function. Here is its graph. Let's say it's kind of curvy, it does something like that. And let's say that we are concerned about a specific interval. Let's say that it's from A to B. Okay, so we're talking about some function. We're going to call it f of x, just for ease of naming things. But we're going to try to find the absolute, or not the absolute, but the average value of it. So let's go back to what you guys define an average to be. An average is you add up all the numbers, and then you divide by the number of numbers. So then, how many numbers would we have to add up on that interval from A to B if we're going to find this average? How many y values are, there's an infinite number of y values between A and B. And so for us to think that we could just go there and just like start plugging numbers in and adding them all up, you're never going to add them all up because there's always going to be another one that's even smaller. So the way that you add up all the numbers with an infinite summation is the integral. So here is me adding up all the y values. Pretty simple. Integral from A to B of f of x dx. That adds up all the y values, and it does it pretty simply. That's just the sum, though. We need to figure out how to divide by the number of numbers. So again, like how many numbers are there in between there? There's an infinite number of them, so how that's going to work, it's not going to work at all. So instead of doing that, what we do is we divide by the width of the interval. So for this particular interval, it would be dividing by b minus a. So if your interval goes from like 2 to 11, you would divide by 9. If your interval goes from like -3 to 12, you would divide by.
No longer wake him up, that would be funny.
I know. All right. So then you probably will see this in a slightly different form that I will typically use more often than not. It looks like this: 1 over b minus a, integral from a to b of f of x dx. This is just looking at it from a slightly different perspective. Essentially, we're getting the constant multiple away from the integral, but it's the same thing as what we just wrote up there. So this is the formula that you would use, and we'll try to use that next. But I want to make sure that that at least seems somewhat logical, like how you add up all the numbers. That's what an integral does. And you divide by the width of the interval. That's like dividing by the number of numbers. Okay, fair enough. Why don't you guys try number 9? See if you can set this up, get some good practice. Again, no calculators. I don't think 9 needs them. So try this without a calculator. See how it goes. All right, so let's see how this goes for everybody. The setup should look like this. Give myself a little more room here. Setup should be this: 1 over 4 minus 1 times the integral from 1 to 4 of 3x squared minus 2x dx. What tells you that you should be doing a setup like that is this phrase here: find the average value of f of x. This formula generates that type of an answer. So that's your setup. Any questions on that part before we try to work on the details of how it goes? All right, so let's try it. Of course, 1 over 4 minus 1 is just 1/3. And the antiderivatives work out pretty nice. Did you guys get x cubed minus x squared? So at that point, we have done the antiderivative. We found it. And so the tall skinny s and the dx have been integrated back in. They're gone, essentially. And we say evaluated from 1 to 4. So what I'm going to do now is plug in the 4 and plug in the 1. We're just going to do that fundamental theorem part 1 like we've done quite a few times already. So it'd be 1/3 times 4 cubed minus 4 squared minus 1 cubed minus 1 squared. How does that second term work out inside? 0. Yeah, it's just a 0. So come up here, it's going to be 1/3 times, what is 4 cubed? 64. Minus, and then of course 64 minus 16 is 48. What's 1/3 of 48? 16. How lovely. I heard that number put out there a few times. So how did that work out for you guys? 16? We happy? Yes? No? Are there any questions? Thumbs up from Ben. We're good. Okay. No questions at all? Are you guys getting pretty good at this antiderivative stuff? The definite integrals? Is it? I hope it's going okay for you. Okay, we're going to finish up right here with a somewhat terrifying question when you think about Billy and his health. Billy is eating donuts at a rate of r of t equals 2t cubed donuts per hour on the interval from 0 to 4. What is his average rate of donut consumption in donuts per hour? So we're going to do something a little bit like what we've done in the Hey guys, a little bit like we've done in the past. I want you guys to read through this again, and this time I want you to underline or highlight any places where you see a rate being mentioned or illustrated. Okay, we're going to try to make hopefully some good connections for you with this, some good connections with what we've done in the past. But just for right now, let's highlight anything you feel like indicates a rate. Here is that you looked at this and said, hey, there's the word rate, so r of t is clearly a rate. The units indicate that as well. But then don't they ask you for an average rate as well? So they're asking you for that in the end. So I'm going to make hopefully a good connection here for you. We'll be able to further make it, maybe in a little bit further into the notes. But for now, let's check this out. Here's what I would do for a setup. I would say my interval is 0 to 4, so I'd go 1/4 times the integral from 0 to 4 of r of t, right? So r of t is a rate. And so if I want to find the average rate, I want to find the average value of r of t. Does that make sense? Sure. Average value of r of t, so they give me an average rate. So to finish this, it'd be 1/4 integral from 0 to 4 of 2t cubed dt. The antiderivative, pretty convenient. Would go 1/4 times, 1/2 t to the 4th. Evaluator from 0 to 4. So that gives me 1/8. t to the fourth, evaluated from 0 to 4. And then we'd complete the FTC1 and finish. So it'd be 1/8 times 4 to the fourth minus 1/8 times 0 to the fourth. So what's 1/8 of 4 to the fourth?
32.
I think it ends up being 32, doesn't it, right? Because 4 to the fourth is 256.
Yeah.
So divided by 8 should be 32 minus 0. That's just 32. What would be the units on 32?
Donuts per hour.
Donuts per hour is correct. So do you see why Billy might have cause for concern for his health? That's his average rate for this time interval is 32 donuts per hour.
For 4 hours.
That's just the average rate. At the end, he's doing way more than that, right?
At the end, he's doing
Like, acknowledge how impressive that is.
It is very impressive. I mean, think about it. At the end of the fourth hour, his rate is 2 times 4 cubed. That's 128 donuts per hour at the end of the fourth hour.
I don't think he'd survive more than a week.
No, he would not. It's like the Super Size Me thing, right? Did you ever see that movie? Where the dude just like orders Super Size McDonald's for like a whole month for every meal or something? Yeah, pretty crazy. Hey guys, I want to make this connection with you. I hope this is very helpful for you. We have seen average rates before, haven't we? Hey guys, this I hopefully will be a big connection for you. I hope. We've done average rates before. So haven't we found like the average slope before?
Oh, yeah.
Remember how we found the average rate of change of, some, I'm trying to think about what we found the average rate of change of, but didn't we do it by doing something like this? y2 minus y1 over x2 minus x1? You with me?
Yeah.
Those of you that have been in the club for a while have found average velocities and average accelerations, correct? Too many times.
Almost.
So I want to make a connection with you that I think will be extremely handy. So let's say there was a whole separate question. Let's say that I gave you a velocity function. Let's say we call it v of t. And then I asked you for the average velocity. I want you to think this through because there's a potential to be very confused here. I want to kind of take you there and try to help you through it. So what's the formula for average velocity?
V2 minus V1.
No, that's not correct. That'll give you average acceleration. Displacement over time. So how would you express displacement?
X2 minus X1.
There we go. So x2 minus x1 over t2 minus t1. But I want to try to bring that up to more contemporary thought with what we just did. If I gave you a velocity function and asked you for average velocity, wouldn't you think that it would be something like this? Maybe like 1 over b minus a times the integral from a to b of v of t dt? Right? If I want the average value of the velocity function, it would be something like that. So then, how do we reconcile those two things?
The integral of velocity is position, right?
So, let me come all the way up here because I can see that the little logo on the bottom is getting in the way. So here's what I'm talking about. 1 over b minus a, integral from a to b of v of t dt. So I want to make these two connections here. From before, do you guys remember what the integral of velocity is, or the antiderivative of velocity? It's a position function. So if I was going to complete this, I'd say 1 over b minus a times, can I represent position with x? If it's moving left and right, x maybe would make sense. So I'm going to write it as x of t evaluated from a to b. So x of t evaluated from a to b, wouldn't that just be x of b minus x of a? Divided by b minus a. Isn't that the same thing as this formula? So I want you to make that connection how the average value of velocity is just another way of expressing displacement over time. Because the definite integral of velocity is just displacement. So we'll explore this a lot, right? We'll try to go kind of back and forth and all around with this and get you all to a good place where you understand it. But this is at least kind of a foreshadowing of that. Okay, just to let you know, in case anybody was thinking, whoa, I totally thought the formula for average velocity was different than that. It really is the same. It just looks different at the start.
You're coming back in the club.
Coming back in the club? Who's coming back in the club?
People that think that.
Oh, you think they should go back in the club? Now be careful with that, because what if you end up thinking something like that?